The striking infrared images were taken this summer by the James Webb Space Telescope. The James Webb Space Telescope, JWST, humanity's most powerful and ambitious space observatory, has once again peered into the depths of the cosmos and made an astonishing discovery, an encounter so perplexing that it defies current astrophysical understanding. In one of its deep field observations, the JWST captured light from a collection of celestial objects whose properties seem to violate the fundamental rules of cosmology. These entities, tucked away in a remote and ancient part of the universe, are not only older than they ought to be but also inexplicably massive and well-structured for their supposed age. This seemingly impossible encounter is challenging the very foundations of the Big Bang model and the timelines that define the structure and evolution of the universe. Before we start, smash the like and subscribe buttons for more updates. The telescope's instrument zeroed in on a region of space that had previously been observed by Hubble but with far less detail. When the JWST extended its powerful infrared gaze into this cosmic patch, it unearthed an assembly of galaxies whose redshifts implied they existed just 300 to 500 million years after the Big Bang. At first glance, this might seem consistent with JWST's mission to observe early galaxies. However, what was startling about these findings was not their age but their maturity. These galaxies appeared fully formed, brimming with stars, showing rotational dynamics, and even harboring early signs of central black holes, traits that should have taken billions of years to develop. The laws of physics, as currently understood, predict a more gradual evolutionary arc for the cosmos. Galaxies are thought to form through hierarchical mergers, starting small and gradually coalescing into larger structures over vast spans of time. Yet the galaxies JWST observed were massive, densely packed, and strikingly evolved. They contained heavy elements like oxygen, carbon, and iron, indicating that multiple generations of stars had already lived and died within them. This implies a level of chemical enrichment and stellar evolution that seems impossible to reconcile with the age of the universe at the time these galaxies are said to have existed. Astrophysicists around the world reacted with a mix of excitement and skepticism. The observations were meticulously checked for errors, instrumental malfunctions, miscalibrations, or even gravitational lensing effects that might distort the true nature of what JWST was seeing. Yet the data held firm. The galaxies were real, and they were ancient, massive, and mature. Their very presence seemed to whisper that something fundamental was amiss in the cosmological timeline, a timeline that had been largely unchallenged for decades. One particularly baffling object, now nicknamed Galaxy X, stood out among the rest. This galaxy, located nearly 13.5 billion light-years away, exhibited a structural complexity comparable to that of the Milky Way. Spiral arms, a bulging core, and a rotational pattern suggested a dynamic equilibrium that should not have been possible so soon after the dawn of time. Galaxy X also emitted a spectrum rich in metallicity, further reinforcing the idea that this galaxy had undergone complex star formation cycles. How could such a structure have emerged in a universe still believed to be in its cosmic infancy? The implications of this are staggering. If galaxies like Galaxy X exist in significant numbers, it would imply that the early universe was far more efficient at forming structures than current models suggest. Either the rate of galaxy formation was dramatically faster than anticipated, or the initial conditions of the universe were not as simple and uniform as once believed. This raises questions about the nature of dark matter and dark energy, which are thought to govern the formation and behavior of cosmic structures. Could our understanding of these elusive forces be flawed? Might there be unknown physics at play that accelerates the growth of early galaxies? One possible avenue of interpretation is that the early universe went through a brief but intense phase of star and galaxy formation that current models have overlooked or underestimated. This epoch of hyperformation might have been driven by denser fluctuations in the primordial plasma or by interactions between dark matter particles that are not yet well understood. If this is the case, then the cosmological models may require recalibration to incorporate a much more chaotic and productive early universe. Another school of thought considers whether the nature of time and space themselves might need reevaluation. Some theorists speculate that what JWST is witnessing could point toward variations in the rate at which time flowed in the early universe. If cosmic time didn't tick uniformly, then perhaps billions of years of internal evolution could occur within galaxies while only hundreds of millions passed from our observational frame. Such a proposition, while radical, opens new pathways into understanding quantum gravity and the nature of spacetime itself. Equally provocative is the suggestion that the standard cosmological model, the lambda cold dark matter, lambda CDM, model, may be incomplete or fundamentally incorrect. This model has been the prevailing framework explaining the expansion of the universe, the distribution of galaxies, and the role of dark energy. However, if mature galaxies are found to populate the early universe in significant numbers, this model might need to be either significantly modified or replaced altogether. Alternative theories, such as modified Newtonian dynamics, MOND, or even cyclic cosmological models, could gain renewed interest as scientists search for frameworks that can accommodate these puzzling findings. The discovery also has implications for our understanding of black holes. The existence of supermassive black holes at the centers of these ancient galaxies is another conundrum. According to current theories, black holes grow slowly over time by accreting matter or merging with other black holes. Finding gargantuan black holes embedded in galaxies that existed mere hundreds of millions of years after the Big Bang upends this narrative. Their presence hints at either a different formation mechanism or an accelerated growth phase that has yet to be accounted for in mainstream theories. JWST's capabilities have made it clear that the early universe is far more diverse and structured than anyone had anticipated. Unlike previous telescopes, which relied largely on visible light, JWST operates in the infrared spectrum, allowing it to pierce through cosmic dust and reach deeper into space, and therefore further back in time, than ever before. Its ability to resolve fine details in these ancient structures is transforming the field of observational cosmology. No longer are astronomers limited to viewing faint smudges in the distance. They can now analyze the internal dynamics, chemical composition, and star formation rates of these remote galaxies with unprecedented clarity. The impossible encounter has also reignited philosophical debates about the nature of the universe. If the laws of physics can be bent, or even broken, under extreme conditions, then the principle of uniformitarianism, which underlies much of scientific reasoning, might need rethinking. Is it possible that the universe behaves differently at different epochs, under different conditions? Are there cosmic variables we've yet to identify that influence how matter and energy evolve? These are not just academic questions, they go to the very heart of what it means to do science in a universe that may be more mysterious and unpredictable than previously imagined. The encounter has prompted a surge in theoretical work as cosmologists scramble to adjust their models to account for JWST's findings. Simulations of the early universe are being rerun with new parameters, seeking scenarios that could yield such mature galaxies so soon after the Big Bang. Theoretical physicists are revisiting old ideas, some discarded, others considered fringe, in hopes that overlooked nuances might offer the missing pieces of this cosmic puzzle. The interplay between observation and theory is now more vibrant than ever, with each new data release from JWST acting as both a revelation and a provocation. As JWST continues to scan the cosmos, the possibility looms that even more astonishing encounters await. Each new observation could further stretch the boundaries of known physics, or perhaps solidify a new paradigm in our understanding of the universe. The telescope's data stream has already hinted at other irregularities, quasars too bright, star clusters too large, and temperature gradients in the cosmic microwave background that resist easy explanation. It seems that this impossible encounter is not an isolated anomaly, but rather the first major crack in what was thought to be a solid theoretical edifice. This new era of cosmic discovery, ushered in by JWST, is marked not by the comfort of confirmation but by the thrill of contradiction. It serves as a reminder that science thrives not when it rests on consensus but when it is forced to confront the unexpected. The telescope's findings are not just discoveries, they are disruptions. Beautiful, complex, and profoundly unsettling disruptions that demand attention, inquiry, and humility. In the vast, silent theater of deep space, the James Webb Space Telescope is a lone observer, uncovering secrets older than memory and more profound than prediction. The impossible encounter it captured is more than just a snapshot of distant galaxies, it is a mirror held up to the limits of human understanding. Every photon of ancient light that reaches its instruments challenges what we think we know about the birth and structure of the universe. And in doing so, it offers something even more valuable than answers, it offers questions. Questions that will guide the next generation of scientists as they strive to decode the riddles written in starlight and shadow. As the cosmic story continues to unfold, the implications of this encounter ripple outward through universities, laboratories, observatories, and into the collective imagination of humanity. The universe has spoken, not with certainty, but with paradox. And thanks to the James Webb Space Telescope, we are finally able to listen with the clarity and depth such mysteries deserve. Meant black holes. Such black holes appear to have formed and grown far faster than theoretical models predict. Their mass, inferred from the energetic phenomena surrounding them, raises serious questions about their origin. Were these primordial black holes formed from direct collapse, a process in which massive gas clouds collapse directly into black holes without first forming stars? If so, the early universe may have spawned a generation of black holes through mechanisms that are still not well understood. Beyond individual galaxies, JWST has also revealed surprising patterns in the large-scale structure of the early universe. Cosmologists have long theorized that galaxies are not randomly scattered but are arranged along vast filaments of dark matter forming a cosmic web. While this structure is clearly visible in the modern universe, its emergence in the early universe was expected to be more primitive and diffuse. Yet JWST's observations suggest a surprising degree of coherence and clustering among these ancient galaxies. This suggests that the gravitational framework necessary for such structures was already well in place shortly after the Big Bang, possibly pointing toward a universe that evolved in an unexpectedly orderly fashion from its inception. Equally intriguing is the diversity among these early galaxies. Rather than a uniform population of similar primitive systems, JWST has revealed a rich variety of galaxy types, from massive starburst to quiescent systems where star formation had already ceased. Some appear to be merging, others exist in relative isolation, and some show signs of being gravitationally lensed by unseen masses. This diversity mirrors the modern universe in a way that current formation models simply cannot explain. It implies that galactic environments, evolutionary pathways, and intergalactic interactions were far more advanced at early epochs than anyone anticipated. A particularly groundbreaking subset of the data comes from JWST's Deep Field Grism spectroscopy, which allows astronomers to measure redshifts with exquisite precision and confirm the distances of these perplexing galaxies. This has eliminated much of the uncertainty associated with earlier surveys, which relied heavily on photometric estimates. With spectroscopic confirmation, the observed galaxies cannot be dismissed as foreground objects or artifacts. Their positions on the cosmic timeline are secure, their implications inescapable. In tandem with the observational data, computational astrophysicists have raced to update simulations of early universe conditions. Advanced cosmological simulations such as Illustris and Eagle had already produced high-resolution models of structure formation. But even their most optimistic scenarios fall short of replicating the galaxies now visible through JWST. Newer simulations have begun incorporating more aggressive star formation recipes, higher gas inflows, and more exotic mechanisms for black hole growth. Yet even these expanded models struggle to fully replicate the extreme galaxies JWST has revealed. This mismatch underscores the urgent need for a new generation of models, perhaps ones that incorporate unknown forms of feedback, different initial conditions, or physics beyond the standard model. There is growing speculation in theoretical physics circles that some of the underlying assumptions of cosmology may be flawed. One area of focus is cosmic inflation, the brief but exponential expansion thought to have occurred a fraction of a second after the Big Bang. If inflation behaved differently, was more turbulent, inhomogeneous, or even anisotropic, it could lead to a universe where structures form more quickly in certain regions. Another provocative idea is that the constants of physics themselves may not be constant. If values like the gravitational constant or the rate of expansion, Hubble parameter, varied slightly in the early universe, it could radically alter the pace of structure formation. Such possibilities remain speculative, but they highlight just how much this single encounter, an unambiguous glimpse at a mature galaxy at the dawn of time, has shaken the scientific community. Theoretical recalibration is only part of the response. Observational strategies are also being rethought. Future observation campaigns with JWST are being redesigned to probe even earlier epochs, pushing toward the so-called dark ages before the first stars ignited. Scientists are hunting for signs of population 3 stars, the hypothetical first generation of stars made almost entirely from hydrogen and helium. These stars are believed to be massive, short-lived, and critical for initiating the chemical enrichment of the universe. Yet they remain elusive. JWST may yet detect them. Or perhaps their absence will itself become another mystery to solve. JWST's instruments are also being employed to investigate the intergalactic medium, the diffuse gas that fills the space between galaxies, to assess its composition and ionization state at these early times. Understanding how and when the universe transitioned from opaque to transparent during the so-called epoch of reionization is essential for framing these galactic discoveries. If galaxies were ionizing their surroundings earlier than expected, it suggests that their energy output was far more intense, again hinting at extraordinary processes at play. One particularly fascinating aspect of the JWST's findings lies in the philosophical dimension they open. These early galaxies, so far removed from us in both space and time, are not just scientific curiosities. They are windows into the formative epochs of everything that exists. The light we receive from them began its journey when the universe was less than 5% its current age. And yet it carries signatures of processes that speak to cosmic maturity. It's as though history is being rewritten in real time, not through speculation, but through direct observation. These are not theoretical constructs. They are real, ancient cities of stars glowing across billions of years to challenge our most cherished models. There's also a poetic tension to the idea that the farther we look back in time, the more developed the universe appears. This inversion of expectations invites reflection not just on the universe's physical nature, but on our place within it. Are we at the center of some grand evolutionary climax, or merely one phase in a universe that has been dynamic and unpredictable since its earliest moments? The impossible encounter caught by JWST demands more than equations and models. It demands imagination, humility, and the willingness to abandon old assumptions in favor of truths that may be stranger and more wondrous than we've yet dared believe. In the years to come, as more time is allocated to JWST's deep field observations, and complementary missions like the Nancy Grace Roman Space Telescope join the effort, the cosmic picture will become clearer. But clarity may not mean simplicity. Instead, it might reveal a universe more layered, intricate, and riddled with paradoxes than ever imagined. Each new impossible object will be another thread in a story that is rapidly evolving from one of order and predictability to one of complexity and astonishment. The unfolding revelations from the James Webb Space Telescope, JWST, have sparked not only scientific upheaval but have also prompted the reconsideration of how cosmic history is conceptualized. With every observation, the telescope penetrates further into the obscure epochs of the universe, and its most recent data sets are beginning to point toward scenarios that verge on the surreal. Beyond the monumental discovery of mature galaxies in an era thought to be dominated by chaos and dust, the telescope is now encountering entities and phenomena that stretch the very limits of comprehension, astronomical configurations that don't just tweak existing theories but seem to originate from an entirely different cosmic rulebook. One of the more startling developments involves the detection of ultra-compact high-energy objects at extreme redshifts residing in regions that theoretically shouldn't have had time to produce such concentrated structures. These are not galaxies in the traditional sense, nor are they quasars or known types of stellar assemblies. Their radiation signatures are unique, characterized by sharp emission peaks, strange polarization patterns, and fluctuations that suggest highly turbulent internal processes. Initial attempts to categorize them as early active galactic nuclei or dense star-forming regions failed under scrutiny. Their properties hint at phenomena that may involve unknown forms of matter or exotic states of physics that have not yet been replicated or theorized within particle accelerators on Earth. These enigmatic objects, provisionally dubbed protoanomons by some astrophysics teams, exhibit gravitational effects on nearby structures that are disproportionate to their estimated mass. This suggests either errors in gravitational modeling or the presence of new physics. Perhaps variations in gravitational strength under extreme density, or even interactions between gravity and dimensions beyond the familiar three of space and one of time. While such conjectures previously belonged to the realm of speculative physics or string theory, the observational solidity provided by JWST is forcing serious consideration of such exotic frameworks. Parallel to this, JWST has recorded high-fidelity spectra from what appear to be early-type planetary nebulae, clouds of gas and dust expelled by dying stars. These features, usually associated with stars in their final stages of evolution, were spotted embedded within galaxies that supposedly predated the full life cycle of even a single stellar generation. The implication is profound. If planetary nebulae were forming just 500 million years after the Big Bang, then stars must have formed, evolved, and perished much earlier than any current timeline allows. This realization is forcing cosmologists to reassess the fundamental clockwork of the cosmos, not merely pushing the beginning of star formation earlier, but radically condensing the life cycles of early stellar populations. Among the most surprising developments has been JWST's ability to observe the interstellar medium within these primordial galaxies with extraordinary detail. For the first time, scientists are witnessing the early universe's gas dynamics, revealing evidence of pressure gradients, magnetic field lines, and complex feedback systems, phenomena thought to require far longer to evolve. These features are not just curious. They are foundational to the behavior of galaxies. The presence of such complexity implies that mechanisms like magnetic reconnection, supernova-driven turbulence, and radiative pressure were already at work during a period previously labeled the cosmic dawn. Moreover, some of the gas flows observed by JWST seem to be moving at velocities and densities that defy hydrodynamical predictions. In certain cases, gases are seen flowing inward and outward simultaneously in patterns that do not conform to any known feedback or accretion models. These gas motions might point to novel forms of energy transfer or to non-equilibrium states that prevailed in the early universe, states in which gravity, radiation, and thermal pressure interacted in ways not yet simulated or modeled. If confirmed, this would necessitate a dramatic expansion of fluid dynamics theory in a cosmological context, potentially redefining how galaxies regulate star formation over time. While these physical anomalies occupy much of the scientific spotlight, JWST's imaging has also uncovered surprising symmetries in galactic distribution across vast cosmic distances. Some observational fields show configurations of galaxies that appear to form regular patterns, geometric alignments, or equidistant arrangements that hint at either statistical coincidence or deep underlying principles of cosmic organization. These patterns challenge the assumption that the universe's early stages were governed solely by randomness and gravitational collapse. Some researchers are exploring whether quantum fluctuations during the inflationary epoch could have seeded these alignments, or whether more radical mechanisms like cosmic topology or large-scale resonance effects could be responsible. Another aspect of JWST's ongoing campaign that continues to deliver astonishing results is its mapping of early supernovae. Prior to the telescope's deployment, supernovae from the first billion years of the universe had never been directly observed. Now, the telescope has captured light curves and spectra from these ancient explosions, revealing energy outputs, decay rates, and element dispersal patterns that differ significantly from later cosmic times. Many of these early supernovae are more luminous and faster evolving than expected, pointing toward progenitor stars that were likely massive, metal-poor, and perhaps formed under conditions unique to that epoch. Some explode with signatures similar to parent-stability supernovae, a rare and theoretical class of explosions that could only occur in stars exceeding 150 solar masses. The implication is that the universe may have produced a class of supermassive, short-lived stars whose deaths contributed to the rapid chemical enrichment now being observed. This wealth of information about supernovae also opens a potential pathway to understanding one of cosmology's greatest mysteries, the formation of the first black holes. If these massive stars collapse directly into black holes without shedding significant mass, they might have seeded the early growth of the supermassive black holes seen at the cores of young galaxies. However, JWST has detected emissions that suggest not all these black holes followed a direct collapse path. Some seem to have formed via dense stellar clusters collapsing under mutual gravitational attraction or possibly through mechanisms involving as yet unknown physics. In a parallel thread of discovery, JWST has been able to measure the properties of the cosmic microwave background, CMB, through foreground lenses in ways that add nuance to existing maps provided by missions like Planck. By observing how ancient light is warped and scattered by early galaxies and dark matter halos, scientists are beginning to discern subtle anomalies in the texture of the CMB, variations that could suggest large-scale inhomogeneities or anisotropies that were previously undetected. These findings are now being cross-referenced with large-scale structure data to determine if there is a mismatch between the smoothness of the early universe and the structure that appeared shortly thereafter. In yet another frontier, JWST's precise measurements of galactic rotation curves and gravitational lensing have begun to yield fresh insights into the elusive nature of dark matter. Unlike earlier observations that only inferred the presence of dark matter through galactic motion, JWST's advanced instrumentation allows for a more detailed mapping of mass distribution. Early results suggest that dark matter may have clumped in the early universe with higher density gradients than predicted. This opens the door to alternate dark matter candidates such as ultralight axions, sterile neutrinos, or even primordial black holes that may better explain the acceleration of structure formation. If you like this video, please give it a like and subscribe to our channel. Also leave your comments below and tell us what are your thoughts on James Webb's discovery. What do you think it found? We want to hear from you. Thank you for watching and see you next time.